The next presentation is an enhanced method of initial cluster center selection for K-means algorithm by Zillur Rahman, MD Sabir Hossain, Mohammad, Hasan, and Ahmed. Imteaj, you can get started.
Thank you. Good afternoon, everyone. I am Zillur Rahman. I will present the article titled by an enhanced method of initial cluster center selection for K-means algorithm. First, the introduction. In K-means algorithm, there are K number of clusters such as C1, C2, Ck, and n number of samples such as x1, x2, and xn. This is the cost function that is used in K-means algorithm, where xj is a data sample of cluster Ci, and a small ci, it is the centroid of that cluster.
Give slideshow so that we can see the full slide.
Okay, sir. The centroid of a cluster can be found using equation 2. And here are the steps of simple K-means algorithm. First, we take K number of random samples as the initial centroids. Then Euclidean distance between each sample and each centroid is computed. And according to the distance, we assign each sample to its nearest cluster. Next, we calculate the centroid of each cluster using equation 2. And then we compute the error using the cost function and take those initial centroids corresponding to the minimum error. Here is the literature review. First, in reference to a very simple initial centroid selection algorithm was developed. The first centroid is selected randomly from all the samples. The second centroid is the sample having maximum distance from its nearest centroid. This process continues until K number of clusters can be found. In reference 3, first, all the Euclidean distance between the samples are computed, and the two samples with the shortest distance are selected. Then these two samples are deleted from the main sample set along with their n nearest neighbor. In that way, a new set will be created. By repeating this process for K times, K sets are created. The mean of each set used as an initial centroid, and those initial centroids then are applied to the K-means algorithm for clustering. In reference 4, a global search technique was developed, which adds one cluster center at a time. This process is repeated until K number of centroids are found, and PCA was used for dimensionality reduction. In reference 5, another technique was developed for initial centroid selection, where all the distances between samples are calculated first. The mean distance and density of each sample are computed using the developed density function. The author designed a new density function in that work. The sample having maximum density is selected as the first centroid, and some neighbors of that sample are deleted from the stored density array. This process is repeated for K times. In reference 6, a simple technique based on the weighted average of the attributes or variables was developed. The attribute values are weighted average for their sample for each sample and sorted out. The sorted list is then divided into K set, and the mean of each set will be the initial centroid. In reference 5, a new initial centroid selection method was proposed. First, all the distance between the samples are calculated. Then the sums of distance for all the points are computed and sorted using their sum of distances from maximum to minimum. The point that has the maximum sum of distance is the first centroid. Then next, n by k, where n is the number of samples and k is the number of clusters, are discarded, and the first sample after that is selected as the second initial centroid. This process will be repeated for k times. And finally, in reference 8, it is based on the furthest samples. The mean of the dataset is calculated first, and the furthest sample from the mean is selected as the first initial centroid. Then the next centroid will be the sample that has the maximum distance from the first centroid. In this study, we propose a new approach to find out the initial centroid. Initial centroids should be far away from each other since clusters are separated from each other. So the first two initial centroids should be also far away from each other. To find the two farthest samples, we can calculate all the distances between all the samples. However, this is a very time-consuming process because lots of calculations need to be done. We can, but as you can see, the two farthest samples have to be sorry, two farthest samples have to be in the outer region of the data set, such as this sample or this sample or these two, or we can consider these two and these two samples also. So now if we can find the coordinate of those outer samples, we can find the first two farthest samples easily. To do that, we used the convex hull algorithm that gives us the coordinate of the outer samples, such as this. Now, if we calculate the distances between only these 7 or 8 points and find the 2 points that have the maximum distance, we can take those 2 points as the first two centers. You can see it in figure 3a. In red marking, these two are our first two centers because they are far away from each other. The rest of the centers will be computed using this equation. Here there are two distances. The first distance is the distance between each sample and first centroid, and the second one is the distance between each sample and the second centroid. Then we will add those two distance and take the sample that has the maximum distance. You can see in figure 3b, this sample has the maximum distance. So we will take this as the third initial centroid. And we will do the same procedure for the rest of the centroids. However, while computing the fourth and the fifth centroid, we encounter a problem. That is, they both turn out to be two previously selected centroids because they still have the maximum distance. And if we do not consider previously selected, such as this one, this one, this one, while computing the fourth centroid, another sample from the same cluster, such as let's say this one or one from this, gets selected. But we do not want two initial centroids from one cluster. So if we only do this, here is the clustering result. As you can see, there are lots of error and we have a very poor performance. Now, to eliminate this problem, we will delete some nearest samples of the previously selected centroid. As you can see in figure 5a, we deleted some samples from here, temporary, and also from here. Then we calculate the third one, and then we will delete some nearest sample from the third one also. And then we will have this fourth centroid. And we will delete some nearest sample of the fourth, and we will have this as the fifth initial centroids. Now we have 5 samples, and we will use them in the basic k-means algorithm. And if we use them, now we have this clustering performance. As you can see, this is an error-free performance. Okay, now experimental results. To evaluate our proposed model, we used 1 synthetic dataset and 4 real-world datasets. This is the result of the synthetic dataset. There are 6 clusters, total 300 samples, and standard deviation is 0.75. As you can see, this is a very good performance with some minor errors. These are the real world dataset. First one is the IRIS dataset. It has 3 clusters, 5 samples per class, and total of 150 samples. The wine dataset, it is also very popular. It has total 170 samples, and they are divided in 3 classes. Each sample has 13 attributes. Since not all the attributes are important, we used principal component analysis for dimensionality reduction. Here is the later image recognition data. It has 20,000 samples and 26 classes. But in this experiment, we only used cluster A and D only, where there is a total of 1,594 samples. And to spinning data, it has a total of 75 instances and 4 clusters. These are the 3 evaluation metrics that we used. First one is the clustering error. Second one is the CCP index. It measures the degree of closeness between the initial centroids and the actual centroids. And the last one is the RAND index that is used to measure the degree of similarity between 2 data clustering. Here we will go through a step-by-step process for only the iris dataset. As you can see, this is the dataset. First, we will compute the convex hull. So we have these outer samples coordinate. Then we will find out 2 farthest samples, that is C1 and C2. And then this is the 3rd centroid. So we will use these 3 samples as the initial centroids and apply them to the K-means algorithm. And finally, this is the clustering result. As you can see, this is a very good performance, except some misclassified samples such as these 2 or these 2. There are total 150 samples and 11 misclassified samples. So overall performance is very good, around 7% clustering error. Here is the discussion part. In table 1, we report the computation time and CCPI for both K-means algorithm as well as our proposed system. If you look at the synthetic data set result, you can see our model performs way better than the K-means algorithm. It takes less time. Also, the CCP index value is very low. However, if you look at the later image recognition data set, you can see K-means algorithm performs better than our system. We found after a thorough investigation that when there are a fewer number of clusters in the data, K-means algorithm works better. It's because there is a high chance that the randomly selected initial centroids are actually closer to the actual centroids. As a result, there fewer number of iterations will be required, which results in less computation time. But when the number of clusters increases, such as 3, 4, or 5, or greater than that, our model performs better because our model selects only one centroid, initial centroid per cluster. So within 2 to 3 iterations, our model converges and it results in less computation time. In table 2, we report the comparison with our proposed model with other related systems. In these 4 real-world datasets, as you can see, our model performs better for all the datasets except these 2, where reference 8 and our proposed model has the equal result. In table 3, we report the RAND index. Since not all the relevant works reported this metric value, we only included whatever we have got. So here's the conclusion. In this work, we propose an enhanced approach to select the initial centroids. Initial centroids should be far away from each other. We designed our model based on this statement. Finding the furthest samples by calculating the distances between all the samples is a computationally expensive process. So we use the convex hull to find out the outer samples. From the outer samples, we can easily find first 2 initial centroid distance from the previously selected centroids. And while computing new centroids, we do not consider the previously selected centroids as well as some nearest samples. From the result of 4 real-world datasets, we can say our approach shows consistent and improved performance. The biggest limitation, there is a limitation in our system. It is that it is prone to outliers. So if you want to apply it, you must first remove the outliers. Otherwise, outliers will be selected as the initial centroids. Here is the reference that we used in our work. Thank you. Now, if you have any question, feel free to ask.
Thank you very much for the presentation. Is there any question from our guests?
May I ask a question?
Sure, of course.
Yeah, sure. Go ahead.
Thank you for your presentation. In the last slides, I guess you said your algorithm is susceptible to outliers, right?
Yes.
I thought the same thing because your initialization is deterministic and you're trying to select the farthest points. So that's why it may be susceptible to outliers, and maybe that's why it gave poorer results than the k-means in the latter data set, right? So
yes, you are right.
And another question, did you compare your initialization method to k-means plus? Because it is very common and it is based on, again, selecting the farthest points, but
yes,
not deterministically, probabilistically it selects.
I believe this is the reference to, I believe this is the K++ method, right?
The second one, you mean?
Yes, reference
no,
to,
not,
I believe.
No, k-means plus is based on, again, the distances. So it tries to select
go to the reference section
points.
for the reconstruction.
Are you talking about this k-means plus the advantages of careful seeding?
Yes, but it does not select randomly. It again tries to select farthest points, but not deterministic not in a deterministic manner, but in a probabilistic manner.
Yes, it doesn't select randomly. It first select one sample, then based on the distance, it selects the rest of the samples.
Right. So you compared your method to this k-means plus also.
Well, the authors of that article, they did not report the metrics that we used in their article, so we could not compare our method with it.
Okay. Thanks.
Thank you for your question.
Thank you very much for the presentation.